Alright, so back to life. Yes, recently the computer is now very stable. Okay, so look at this combined loading right here. Okay, yeah. If we have all of this together, so what do we do if I still want to make use of? Basically, if I still want to make use of the criteria that have derived for a fluctuating type of loading, what type of things we have to do, right, in order to do that? So what we need to do is let's consider this, right? We need to use that actually the DE theory to come up with the equivalent value here. So let's say I'm going to draw a stress element. Okay, so here's a stress element out of here, and here's some situations here. Sigma A, tau A. So I'm going to divide this stress element into two parts. One is to deal with sigma A and a tau A at here. Okay, so sigma A is the amplitude; it's a normal stress, and when we design a shaft or design certain elements, the type of cause that can give you this normal stress, okay, it could be basically a normal stress from, for example, sigma A from axial loading. Okay, so you could have an oscillating axial loading to generate sigma A. You could also have sigma A coming from, of course, bending. Okay, right? So when you take a stress element and looking at the location of the element, the possible sigma A could be from an axial loading or could be from a bending. Okay. At the same time, of course, you can have a shear stress. Okay, I should draw it horizontally. Okay. So at the same time, you can have a shear stress at here. So this shear stress, okay, let's call it tau A, and that, of course, could be from bending too. Okay, so basically, could be from or torque or torsion, right? Sorry, I said not bending, torsion. Okay, there's torsion here. Good. So if I look at the type of source for sigma A or tau A, this is the source, okay, contributing to this. Okay. Now, if the particular location has stress concentration factor, or is it let's say it's a fillet location, a notch location, then in front of these values that are here, and you could you will have to multiply. For example, this one, this is Kf, so you're going to have to multiply this value with a fatigue stress concentration factor, and here you're going to have to do the same thing. You're going to have to multiply a fatigue stress concentration factor here, right? So that's Kf of axial. This is Kf for the bending. Yeah. Torsion, same thing. You will have to multiply. This time we call it Kfs, right? Fatigue stress concentration factor. This will be for the torsion type of loading. Okay. So that's the possible source for sigma A and a tau A. Similarly, for the same stress elements, okay, there might exist also the mean value component, and you can have very similarly, you can have a mean value here contributed by axial, mean value contributed by maybe bending, okay, and same thing, you can have a mean value, okay, contributed from torque and tau m, which is from torsion. Okay. And of course, if the location has fatigue stress concentration factor, then you have to multiply the Kf right here. So that's the situation right here. Given a stress element that is under combined loading, I'm separating basically the amplitude component from this mean component. Okay? Yeah. I'm taking all the possible sources into consideration, okay, and then put it over here, right? Okay. Then from here, the idea is, okay, I want to recycle, for example, I want to recycle the modified Goodman line, right? Recycle is I can't directly replace the original sigma A, sigma M. But what I can do maybe is, here is a stress element. I can somehow come up with a sigma A prime using a von Mises stress formula. So from the state of stress at here, calculate a prime component. So this one here is from using the von Mises stress formula. Okay? Yeah. So von Mises stress, basically, if you recall that when you have a stress element with certain stress distribution, okay, along each side, you can calculate the sigma prime, right, based on that stress element. And same thing at here, we could calculate sigma m prime, using the same formula from Mises stress formula. Okay. So if we can do this, right, we get a sigma A prime, sigma M prime. This is just in terms of the A and M now. Then we can substitute basically into the, for example, modified Goodman. So we get sigma A prime over SE, then plus sigma M prime using over SUT, and that equal to N over 1 over this safety factor at here. Okay. So this is the point, this is the idea of how we can recycle this modified Goodman in here. If you have a combined loading, try to get a sigma A prime first, a sigma M prime, and then substitute into this modified Goodman line equation, we can calculate the safety factor. Okay? Yeah. So this is the flow of the thoughts at here. So how do we calculate sigma A, sigma M prime using the von Mises stress formula? So here are the formula here, okay? Yeah. Before I write down the formula, coming back to this formula, to the modified Goodman line here, for the SE, okay, for the SE at here, if you recall that SE is endurance limit, and when you calculate S endurance limit, you know the SE equal to what? KA, KB, KC, and then probably KD, and then times SE prime, right? And one of the factor here is a KC. And KC factor, if you recall that, is called loading factor, right? It's a loading factor. And KC at here, you're going to take it as 1 because this is combined loading. So we take KC as 1 when we learn that those are marine factors, right? For the loading factor, KC equal to 1. Okay. As a matter of fact, I'll explain this a little bit after we write down sigma A prime, sigma M prime. Okay. So it's for now. Just remember, when you calculate the SE, you will set the KC to be 1 for combined loading. Okay? So coming back to sigma A prime and sigma M prime. For the sigma A prime, using von Mises formula, here's the von Mises formula here, okay, for calculating von Mises stress. Okay, so here you have a KF for bending, and that times the sigma A for the bending, and then plus the KF for the axial, okay, then times sigma A axial component. And then we have to divide here a 0.5, which I'll explain it, and square here, plus 3 KFS for the torsion, times tau A for the torsion square. Okay, and then finally everything, the whole thing here, square root. Okay. See, this is the formula for sigma A prime, okay, for sigma A prime. And sigma M prime, okay, very similar. It's not exactly the same. So you have a key F at here for the bending, and this is sigma M bending component. Key F for axial, and this is sigma M for the axial. Okay, that's right. Here is sigma M for axial square, then plus 3 times PFS torsion component. Okay. Alright, so this is the formula for calculating sigma A prime and sigma M prime. Okay, so good? Yeah. Just comments here, okay? So basically, we'll look at here why this is there's a divided by 0.5, okay? I'll make a few comments so you'll see why. So let's consider a very, very special case. Okay, so we're talking about the fairly general combined loading, but from this combined loading equation here, let's consider a very general case. Let's consider if there's only axial. Okay, so consider only sigma A axial. So nothing else but just the sigma A here, and it's contributed by axial loading. Is that okay? So consider only this one here. So if this is the case, so what does that mean? Basically means you have, let's for example, you have a shaft right here, and then you have a loading force, let's say F. So FA is a force basically like this, right? And it's oscillating completely reversed axial loading, and that results in a completely reversed normal stress axial loading. Okay. So if only this one exists, what does that sigma A prime become? Right, what does that sigma A prime become? So if you look at this formula, so that doesn't exist, that doesn't exist, so only this term exists at here. Okay, and this is to the power 2, and then here is 1 over 2, so square root. So the sigma A prime basically becomes what? Just the key F value times sigma A axial and divided by 0.85, right? So that just becomes this. Does that make sense? Okay. So if only this one exists, and what type of loading condition this actually? So sigma M prime is 0. Sigma A prime is not 0. So this essentially is a completely reversed loading, right? And then when you apply to the modified Goodman line for calculating safety factor, and that safety factor equal to what? Okay, just equal to SE over sigma A prime. So substitute this sigma A prime over here. So we get 0.85 times SE and over this KF times this sigma A axial. That makes sense? So then maybe maybe you have a notch somewhere here basically, right? So that'll give you this KF value. Okay. Yeah. So now if you look at this final formula here, see that point A5 shows up in front of SE, right? So what did I just say for calculating SE? When we calculate SE, we use a KC equal to 1, right? Equal to 1. But if you recall that when we learn the marine factors for the SE, And if the loading is purely axial, the Kc is actually what value? I'm not sure if you recall that. The Kc is actually what? 0.85. Okay? So that's where the 0.85 shows up right here, right? There's nothing contradict to each other, basically. Okay? Yeah. So second comment set here, right? So second comment here, let's consider, okay, pure shear. Basically, there's nothing else, just the tau A torsion only. Okay. So only tau A torsion. So if there's only tau A torsion in here, that sigma A prime, if you look at the formula, becomes a √3 times Kf torsion times tau A torsion, right? So Kf torsion times tau A torsion. So your safety factor Nf will become Se over sigma A prime, which is 1 over √3 times Se, and then divided by Kf torsion and tau A torsion. Right, so this is the formula for calculating safety factor here, right? Yeah. Remember, the Se is still calculated with a Kc value equal to 1. Okay, is a Kc equal to value to 1. Now, what is the value for 1 over √3? It's approximately 0.577, right? Yes. Oh, KFS, yeah. Symbol-wise, because of torsion, so KFS, good, yeah. So 1 over √3 is 0.577. So now to jog your mind, when you calculate Se using Kc Se prime, if it's a torsional loading only, that Kc, I'm not sure if you remember, that Kc for torsional loading, that Kc equal to 0.59. So it's very close to this 0.577 right here, right? Yeah. And this is 0.577 is actually part of the von Mises stress basically theories, right? Formula. Okay. Yeah. So this is sort of give you an idea how these numbers actually right conforms with all the different parts of the theories, right? Yeah. Okay. So these two formula, okay, serve you as the important part for combined loading. Calculate these two, substitute into the modified Goodman line or any other lines, and then you'll be able to calculate safety factor. One more thing here, and then we'll look at an example. Is the first cycle yielding under this combined loading. So here's the combined loading, and what will be the first cycle yielding formula? So we can use this formula here to calculate the first cycle yielding. If you recall, if it's not combined loading, if it's just a fluctuating type of loading, for fluctuating type of loading, the formula is SYT over sigma A plus sigma M, right? Okay. So now we're using SYT over sigma A prime plus sigma M prime. Okay. Yeah. Now this is not the precise formula actually. Okay. Yeah. Because we're talking about first cycle yielding. It's like the static basically analysis here. So you use SYT divided by the maximum value. So amplitude plus the right. So maximum basically. So you have a sigma M and then sigma A. So sigma A plus sigma M is this portion here, right? It's this portion. So there is this actually so-called true max. Okay, so true sigma, I call it true sigma max. Okay. So the true sigma max are based on sigma A, sigma M, tau A, tau M. It's like if you have a stress element, and then you have a sigma A, you have a tau A, and then you have a sigma M, and then you tau M also. So you put everything basically into this stress element, right? So you have a sigma A, sigma M, tau A, tau M on the stress element. Okay. Then using the von Mises formula, the true max is actually sigma A plus sigma M squared, right? This plus this. So that's plus the get maximum there, and then 3 times tau A plus tau M squared. So this would constitute the actual von Mises value, right, based on this state of stress. Okay, and then you can say, okay, the n equal to SYT over this sigma max prime. Okay, yeah. So this one here is called the true max. So one of the assignments will ask you find the true sigma max prime, then calculate this one here. Okay, but the true maximum, okay, in theory, okay, you can actually derive the sigma A prime, sigma M prime, okay, in general is greater than sigma max prime. Okay, so this one here in general is greater than sigma max prime. Yes. Tau M. Yes. Yeah. Very good. So you can calculate the true max, not a problem at all. And then you can use this one to get your safety factor. Okay, that's like a D theory. Okay. But in general, this formula here is actually more than the calculation using this formula. So basically, you can see now this one here, the calculation in this one here will actually result in a slightly less safety factor, right? Or in other words, this is a little bit more conservative, basically. Okay, so conservative is fine. You know, we like conservative, and this is also save us time for calculations like this. Okay, yeah. So let's take a look example here. Okay. Okay, let's see, we have a bar here with a notch in the middle. Okay. Suppose that we have all of the parameters here. So this is a more of a a theoretical type of calculation, not a very detailed calculations here. Okay, so we don't need to. I'll just show the steps here how you apply these kind of situations. Okay, yeah. So here's a loading condition. It has a pulsating torque, okay, and the torque varies from 20 to 160 Newton meter. Okay, at the same time, it has a steady bending moment. Under 50 Newton meter. Okay. Yeah. And the shaft is a stationary shaft, so it's not rotation. It's not rotating here. Suppose the material SUT is a 440 megapound, and the SYT is 370 megapound. And SE is 160 megapound. And there are some other parameters, there's some other values we need to calculate. Okay, but anyway, so let's say this is the material here. Okay, so we wanted to calculate the fatigue safety factor at the critical location. Okay. Critical location obviously is the location at the notch location, which is this location here. Okay. Yeah. But first of all, based on the given loading condition, right? Based on the given loading condition, we can examine, what exactly that falls into the three categories: complete burst, fluctuating, and combined loading. So let's take a look at the first statement. It's a pulsating torque from 20 to 160. If I illustrate this one here, basically means you have a torque applied to the shaft, okay, and the torque is changing from 20 to how much? 160. Okay, so this is your T at here. So the T changes from 20 to 160. So apparently you will be able to get to see, okay, so this is a fluctuating type of loading at here for the T, right, at least. Okay. So your T max is 160 and the T mean is 20. Okay. So I can calculate my mean value Tm, which is T max plus T mean over 2. So 180 give us 90 millimeter. And we can calculate the magnitude. 160 minus 20, 140 divided by 20, so 70 newton meter. So that's the torque portion, right? That's torque portion. Second statement, steady bending moment. So the torque is applied as a steady bending moment, 150 newton meter. So basically, it means what? The amplitude of the torque, the bending moment, will equal to 0, and the mean value of the bending moment will equal to 150 newton meter. Okay. So you have a Tm, Ta, you have Mn, but we don't have Ma at here basically. Okay. Yeah. Then we're ready to basically, okay, if you have a torque, you have a bending moment, so that'll give us the tau m not going to be 0. They're going to give us tau a not going to be 0, and this sigma a due to ma will be 0, and the sigma m due to mm, that will not be 0. Right. So that gives us the overall idea for all the components of sigma and tau, and this is apparently a combined loading case, right? You have a combined loading here. So we need to basically use our formula to calculate our combined loading situations. Okay, so we can calculate tau a at that notch area. So this is the formula for calculating tau a. Tau a is directly related to the torque Ta, and also related to the fatigue stress concentration factor at the notch area. So I'm going to skip some steps here. So of course you have to look at the notch sensitivity, the static stress concentration factor, and then you can calculate the fatigue stress concentration factor, right? Yeah. So let's suppose somehow I already find it and I put it into TA, and the small d is the section diameter, right, at this notch area. Okay. So you'll be able to calculate this one here. Okay. So this is just a theoretical. Assuming with the calculation I'll get this number at here, and similarly you can calculate tau m, and that will give me this number. And then we can calculate sigma m So this will give me this this number here. Okay, so this is an example I exerted from another big example, basically. Okay. Yeah. So anyway, so let's suppose with certain fatigue stress concentration factor, and then we'll be able to end up with a number like this and this. Okay, for tau A, tau m, and sigma m. And then once we get this, we calculate our sigma A prime. Okay, sigma A prime. There's only tau A component exists, so that basically just 3 tau A at here square 1/2 square root give us 28.2 megapound. And then you calculate sigma m prime, which is sigma m squared plus 3 tau m squared 1/2 100.6 megapound. Right? Okay, those are directly applications of the formula for the sigma A and sigma m. Okay, finally, you can calculate the okay, so you can calculate safety factor now. So NF equal to 1 over sigma A prime over SE plus sigma M prime over SUT. You know what? I don't have numbers for this one here. You can try it. Plugging all the numbers here. SE is given, right? SE is 160 megapounds, all given in here. So it's probably 2 point something. Okay, so 2 point maybe 2.6 or 7 something. Okay. So this is used in modified. If you choose a different formula, then you get a different fatigue safety factor. And we can also calculate first cycle yielding. So NY in the first cycle yielding NY equal to NSY over sigma A prime plus sigma M prime. This one is approximately 2.87. Okay. So here's the formula. You know, remember I give you 2 different ways of calculating the first cycle yielding, right? For combined loading, this is one way of doing it. Okay. If you wanted to use the true max, so if you want to use the sigma max prime, the true one, the true value. So in this case, given the existing stress, it's sigma m prime plus 3 tau A plus tau m squared, okay, like this. And then you can use your SYT divided by this true max prime, one mid-size. So that should be about approximately maybe 2.8, slightly smaller. Sorry, actually, yeah, slightly bigger probably, because this is bigger than that. So you should get a slightly bigger value, 2.9 something. Yeah. So that's the typical procedure, right, for combined loading. Okay. Identify what type of loading exists, and identify what type of stress they lead to. So look at Tm value, Ta value, Ma value, Mn value, and then that leads to the tau A, tau M, tau sigma A, sigma M. And if there is fatigue stress concentration, then you have to find it out appropriately. And once you find it out, use the formula for sigma A prime, sigma M prime to get the equivalent to more mid-size stress. Once you get that, then you can apply it to the fatigue theory formula to calculate the safety factor. Okay. Yeah. So that's the typical process for combined loading. Okay, any questions? So that essentially sort of finish what we have learned so far in terms of the failure theories for both the static and fatigue loadings. Okay. Yeah. As you aware, we have a midterm on the Thursday. Okay. So maybe I'll just quickly jog your mind at here, without going into the details. Okay. Basically, what we're going to cover in the midterm. So if you recall so far what we have learned, okay, so we did a review on stress, right? So the stress essentially what type of stress, what type of loading caused the stress, and where is the maximum location, right? You have a bending normal stress at the top and the bottom edge of the shaft. You have a bending shear stress, which is on the neutral axis location. So if you have a shaft, so here, right, are the due to the bending moment, and here, right, is due to the shear force. Okay, so they cause a different minimum and a maximum at a different locations. Okay, yeah. And of course, you could also have a torque applied to the shaft. So the torque really doesn't matter. Everywhere on the edge will have the maximum. Okay, yeah. So that basically brings us to examples, and through examples. And I have identified to you guys that if you have a question like a shaft, the critical location, right, are typically at this location, which is the location caused by the bending moment, because they tend to be more critical than the stress caused by the shear force, which is this location here. Okay? Yeah. So basically, when you analyze for the shaft, okay, you don't need to always look at this location and this location. You can always just simply look at this location like that. Is that clear? Yeah. So that's the stress part, right? And the second part, more of from basically solving a standard question point of view is you need to be able to have a free body diagram, right, to draw a free body diagram. This is particularly true for a shaft, right? You have a shaft question. We have a different question in assignments, and you have a different loading conditions, right? Then how do you draw basically the free body diagram? And from the free body diagram, the free body diagram mostly will give you basically, if you have a force at here, then basically you're going to be able to say, okay, what does this supporting force equal to, and what does this supporting force equal to, right? Solving those things from the free body diagram, and then from here, from the free body diagram, you can naturally just basically ask yourself, how do I calculate the bending moment at a certain location on the shaft? So, for example, then you probably identified, okay, so here is the critical location. Okay, here's a critical location here. Then what is the bending moment at that location? How do you calculate the bending moment at that location? Yes. There you go, right? So R1 times the distance from here to here. So here you have M equal to R1 times the L. Okay? So the point here is basically of course, sketching the bending moment Okay, sketching the bending moment diagram is necessary. It's a necessary skill to have. But in terms of calculation, okay, then often in time you don't need to, always sketch out the whole bending moment diagram along a certain shaft. Okay, right? Yeah. So really all you care is just critical location, right? Yeah. And then from here, that basically will bring us to the question. This is basically ask yourself, static loading or not, right? Is it static loading or fatigue loading? Okay. So this is a big question you have to ask yourself before answering the question. And then often in time I find that sometimes students actually confuse the question. A question is static, but then he started to use fatigue loading formula, right? The question is fatigue, and then it's just considering static. Okay, yeah. So if the shaft is not rotating and the force is not it's a constant force, it got to be a static loading, right? Yeah. If you have a stationary force but the rotating shaft, then that's actually going to be a fatigue loading case, right? Yeah. So got to ask this question here. When it's static loading, right? And then you have to ask yourself, is it a ductile material or is it a brittle material? Okay? Yeah. So if it's a ductile material, and we only learned so if it's ductile material, how many failure theories associated with the ductile material? 2, and one is called MSS and DE, right? Good. If it's a brittle material, how many? 3, yeah. And one of these MNS and BCM and MM, right? Okay. And the further consideration, there's another consideration here, I think in the middle of it here, when you, either one of the theory that you choose to do, okay, yeah, there is one more factor that you also have to consider, which is what? Stress concentration factor. So basically you have to consider, do you need to apply the stress concentration factor or not, okay? That's a question mark. It's not necessary that you need to do that, right? Only at location, if the part has a location as a fillet, has a location notch, then it's a static load, and then you apply the stress concentration factor, right? Yeah. And then you have to think about how do you find that stress concentration factor. There's appendix A-15. Okay. There's different figures in A-15. You have to use the appropriate figure. Appropriate meaning that's the figure corresponding to the type of loading, right? Yeah. Yes. Oh yes, very good. I'm just trying to get it here. Yeah. Basically, which do you apply stress concentration factor? Ductile or brittle? Right. It's only the brittle here. So I guess my bracket here is too big. So only for brittle material, right? Okay. Yeah. Only for the brittle material. So if you think along that line there, I think it's a fairly procedural type of things to follow, right? Yeah. But however, the most important part, as I say, is you got to do the first step right, right? Yes. Yeah, I will. Yeah, but you can, if you don't trust me, you can include that in your formula. So that's fine. Yeah. So I will include as much as possible, right, for you to solve, to save you time, basically looking up the tables or looking up at values. Yeah. Yes. Sorry, bring what? Oh, you mean what is ductile, what is brittle? Yeah, you're supposed. I mean, steel is ductile, cast iron is brittle. Yeah, that's basically all we differentiate. Yeah. Carbon steel we consider that as ductile. Yeah. Yeah, if you think about the static loading, that's it, right? Yeah. And then when it comes to the fatigue loading, okay, and there what happened? What? So when you look at the fatigue loading here, if you think about it, first step, okay, is what does the SE equal to, right? And SE equal to basically, so now as I said in the midterm, it only covers until the completely reversed loading, right? So that's the what midterm covers to until lecture 8, which is basically assignment 1 to 3, right? Number 3. So you have to be able to calculate the SE, okay, based on a series of marine factors. Each one of the factors, just like what you just pointed out here, if I will incorporate some of the figures, but I won't tell you what they are. Okay, so you have to know how to use it, what each figures are in the exams. Okay, so you have to identify yourself. For example, okay, I need to apply the temperature factor. Identify, for example, the loading factor. You know, that kind of things, right? Yeah, or size factor or surface factor. Okay, yeah. So once you get this one here, and there's another step, is basically same question you have to ask yourself. How about the fatigue stress concentration factor? And we call that KF, right? And the KF calculation has 1 plus Q, and then KT minus 1, right? And the Q is the notch sensitivity, okay? Yeah. And KT is this factor. KT is from here, okay? And then okay, and once you get this, and if you calculate safety factor, that's basically KF times the sigma A, and you get your basically safety factor, right? Yeah. And over this part of fatigue loading, okay, there's another possible question that here is, okay, I wouldn't call it step 3. Okay, there's another knowledge point that here is within the fatigue loading, is to estimate the number of cycles. Okay, number of cycles n basically equal to what? N is equal to sigma A over A and then to the power of 1 over B. So if you have a certain amplitude of completely stressed, a completely reversed loading, and it depends on the value, and that n could be infinite, value more than 10 to the power 6, or could be less than 10 to the power 6. And typically, we'll ask you to estimate the number of cycles when it's not infinite number life, right? Yeah. So, and what's the formula for A? What's the formula for the B? And then how do you calculate this n here? That make sense? Yeah. So that's another type of question here, right? Yeah. And then also, I'm not sure if there's one question assignment I can remember clearly. The other direction could be asked is, you are given a certain life, for example, right? You're given a certain life, and then you will be asked for what will be a suitable, for example, maybe a force or torque. Sorry, not a torque. What would be a suitable, for example, a force, right, to give you that type of life. So that force will cause this, and then basically result in a certain life, right? So there's different directions approaching this formula here. Okay. Yeah. So if you think about it, that's essentially what lecture 1 to 8 covers so far, right? Yeah, it's not too much actually. Okay. I think I specifically said you can have a one-page formula, double-sided, and but no examples. Okay, formulas only. You can also bring the handouts for the summary on the static failure. There's also one-page handouts on that the general loading condition, but that one page there's not sure actually you need that page. That probably really. You don't need that one there. But yeah. So anyway, so the 2 class handouts plus the formula sheets, and with your calculator and your pencils and erasers. Okay. Yeah. Is that okay? Yes.
When you say no examples, can I put like a free-body diagram of the concept, not like an example with numbers or anything, just a free-body diagram showing the concept?
Free-body diagram on what type of system?
Like the little shear cube and those things.
Oh, like a stress element, you mean?
Yeah, stress element and like.
Yeah, that's fine. That's related to your formula. That's okay.
It's not like an example.
Yeah.
But it's like a diagram. If that's allowed.
Yeah, I think that's okay. Yeah, if it's just a stress elements. Yeah. Like example, basically, you draw a shaft. You like the type of example we have gone through in the class, right? Yeah. I don't think that's going to be allowed. I'll just walk around, because in the past I've seen sometimes students basically put roughly half of some examples in the assignments or in the lecture notes into the formula sheets, right? And I have to turn it off. So is that okay? Yeah. Yeah. So. Don't be too stressed out. Well prepared for the assignments. I think you should be okay, right? Yeah. There will be, if you look at essentially what I just covered, how many? There are essentially like 3 major topics at here, right? Yeah. So I'll pick a question for each major topics. Yeah. Yeah. It'll be actually simpler, I think. Yeah. Because assignments, you need to look up the tables in the textbook, right? In exam, I'll try to simplify the process. Yeah. But you need to know what procedure to follow, though, right? Yeah. Good. Yeah. All right. So, you still have a lot of time. Yes. I think I just said it. 3. Yeah. Yeah. Okay. So you should have enough time, 80 minutes, but I think it's still tight. So that's nature midterm, right? Yeah. Okay. Yeah. Okay. So I still have a little bit of time. I just want to start this next topic, which is introduction to gears. Okay. So you can relax. There are a few slides that are here to talk about the gears. We're essentially going into the topics on different type of machine elements now. And for this section, we're going to look at the gear in particular. There are a few type of gears we're going to look at it. Spur gear, helical gear are the 2 type of gear we're going to look at. Bevel gear, worm gear, we're going to introduce to these 2. Okay, but we're not going to look at the mathematicals in detail for these 2. Okay. For spur gear, we'll cover a lot in details. We will also emphasize on the velocity ratios for different gear trains. Okay, and the most important part is we will use the smashing force on a pair of gear, and use that for shaft design, for gear size design, and later also for bearing selection. So this part here, when you have a gear, shaft, and the bearing, these three things, plus the case, the four things, basically we're going to cover that in one sequence, just like the sequence showing in here. So this is essentially the diagram at the beginning of the term, and I showed you. We categorize the different components, different machine elements into different blocks. So this block here is rotation to rotational for transformation mechanical power, and that includes the gear, bearing, shaft, and the key at here. Okay, yeah. So we'll finish this portion, and once we finish this portion, and you actually will be able to start your project, the course project. Okay, yeah. So sometimes in the near future, I'll post the project requirement. Once we finish this and as a group, then you can basically start planning. You'll have probably about a month to finish the project when we finish this portion here. Okay, so there should be enough time. Okay, so there's an important person that we have to talk about. Basically, if we have to talk about the gear, okay, and this guy is called George Grant. Okay, and the picture showed it here. And in 1876, okay, and there was a centennial exhibit in Philadelphia, Pennsylvania. In that centennial exhibit, and there is this humongous, basically, machine at here, which is called Grant's difference engine. And it's about 5 feet to 8 feet, and it weighs about a ton. It's very heavy. And what it does is, it's a calculator. Okay? It's a mechanical calculator. It's like a 2 plus 2 give you 3, that kind of things. Okay? Yeah. And it's amazing, you know, at that time, right? It's a mechanical calculator, but it works, and it works perfectly. And as a matter of fact, a lot of people right now are actually trying to reverse engineering this mechanical calculator. If you Google and YouTube, you'll probably find some videos on this topic at here, right? Yeah. So now he didn't become a father of computer though, right? You know, he becomes the founder for basically initially it's called I think it's called what company is that? American Gear Industry. Initially it's called what company is called again? Anyway, so that company is gone, but right now the company name is called Boston Gear. So that's the biggest one of the gear company. So basically becomes the founder of American Gear Industry here. Okay. Yeah. Now, in fact, just think about it. It's quite amazing. He worked out essentially most of the mathematics behind the gear, right? And that requires a lot of work essentially. This first type of gear we're going to look at is the spur gear. Okay? So spur gear is the simplest type of gear of all. What it has is it has basically parallel teeth. The teeth is parallel to the shaft. So this is a shaft rotation, and you have a number of teeth. So the teeth are parallel to the axis rotation, and it's typically used to transmit power from one shaft to another. So basically, you have another gear on the top, for example, and then you have another shaft. So the smaller gear probably driving this big gear. So the power transmit from here to here, right? Yeah. So it's a simplest type gear type. Okay, and you see that spur gear actually a lot often in the transmission box. Okay. Yeah. Helical gear, okay, is another very common gear. Okay, and now the difference is basically the teeth, okay, is not straight anymore. Okay, the teeth is sort of inclined to the axis of rotation, and mathematically the teeth, each one of the teeth, okay, is actually basically, okay, if you extend that teeth, okay, it's actually part of the helical curve. So, in the previous courses you learned what a helical curve is, right? If you take a small segment, okay, small segment of this helical curve out, and that's basically this portion of the profile at here, okay, the helical gear. It's also used to transmit power between two parallel shafts. Okay. And because the teeth is inclined, and so the meshing of the two gears, okay, will become more gradual, and the contact ratio, okay, the contact ratio will be higher than the spur gear, and so the motion for helical gear will be smoother actually than the helical gear and than the spur gear. Okay, yeah. It can also typically carry more load than the spur gear. But the difference is, when another helical gear meshing with this one here, it not only generates so-called radial load, but also a so-called thrust load. So, for example, right, if I go back to the trouble. The computer froze. So, for example, if you look at this one here, let's say if I have a gear on the top, small gear on the top, and then meshing with the small gear to here. So there will be a force from the top pushing this one here, and that force will be actually basically in the so-called this is basically the action-reaction force. Okay, and there will be a force in this direction. There will be a force in this direction. Okay, yeah, and so these two forces we call that radial load. Okay, so basically there's no force in the axial direction here. Okay, yeah, but the helical gear is different, and when you have two helical gear meshing with each other, okay, and there will be three force components. One goes, horizontally, okay, this direction. Another one goes along the axial direction, okay, and there's another one goes, perpendicular to the axis. So there will be a force basically going along this axial direction, along the shaft. Okay, so in that particular case, when you design a shaft, then you have to have a so-called thrust bearing to take this to be able to resist the thrust force, the thrust loading at here generated from the meshing. Okay, yeah. So that we'll look at it later, right, for the force analysis. Another type is called a bevel gear. So the bevel gear, the pitch surface is a cone. So what the pitch surface basically means is, if you have a triangle, then if you have a cone, you cut off the top of the cone here, and then you are left with this frustum of this material here. So this is basically what we call the pitch surface at here. Okay, this is the pitch surface. So that's where the teeth are being generated along this pitch surface. Okay. And they're used for transmitting power between intersecting shafts. So you have a shaft here and a shaft here. So these two will intersect at a certain point. Okay. And the two shafts often in time are 90 degrees from each other, and they could be actually any angles. Okay. Yeah. So that's the bevel gear. This is the most common gear you see in automobile differential drive. Okay. But nowadays, the differential drive a lot of time are using this so-called spiral bevel gear. So instead of straight teeth, so the spiral bevel gear basically is this gear teeth is the same as the helical gear. So the profile is helical, part of the helix. Okay, so that's spiral bevel gear, and the two axes still intersect with each other. And of course, because of the helical type of profile here, so there will be less vibration, and it can also take more capacitive load, basically. Okay. Yeah. Another type is called hypodal bevel gear, and for the hypodal bevel gear, the profile of this gear tooth, okay, are based on the so-called basically. So they are based on this hyperbolic profile. They are not conical. So hyperbolic profile, if you look at the profile here, they're more like this kind of a shape, okay, on the surface over there, okay. But the beauty of this one here is you don't need to basically have two intersecting axes of rotation anymore. So the driving shaft could be slightly offset, okay, from the other shaft. Okay. This would actually give you an advantage in terms of the manufacturing, basically how that driving shaft to the rear wheels, and how that can avoid some of the potential basically problems when you design for vehicles, especially designing for the vehicle, the passenger rooms. Okay. Yeah. So those are the different gear, and the last gear is called the worm gear. Okay. So worm gear, it's usually either right angle drive or left is actually it's okay. Yeah, it's okay too. Okay. The difference basically the worm gear is you have sort of like a helical type of profile here. It's more like a screw basically. Okay, so like a screw here. In essence, okay, so this is called a worm. Okay, this is called a gear. So in essence, this one here, there's only one number of teeth. Only one number of teeth. So you see that one number of teeth goes right all the way to the other end. So here you have an n number of teeth. So that gear ratio is n to 1. So this one here, you can actually have a very high gear ratio compared to other type of gear, a pair of gears. Okay. But the motion at it here, instead of the rolling motion, it's a sliding motion. So it generates a lot of friction, a lot of heat. So you typically need a really good lubrications for heat dissipation, right? Yeah. So that's the shortcoming for a part of the worm gear. Okay. So this is basically all the different type of gear. I think in the next lecture we're going to do, I give you a handout. So we're going to basically look at different gear terminologies, right? And we'll write it down together on the piece of paper. Okay. Any questions? Okay. So please arrive a little bit early on the Thursday afternoon, and I'll try to come here early too, so we can, as long as we distribute a paper, then we can start the exam if we can start early.